Swayam Prabha. Digital India. Educated India.
Welcome to Organic Chemistry Paper 3. In Unit 3, we are studying about heterocyclic compound. In Lecture 6, we are going to study about pyridine and pyrimidines. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha MHRD, New Delhi. The topics that will be covered in this session include synthesis of pyridines. We will be looking at how pyridine can be synthesized using Hantzsch pyridine synthesis. We will also be looking at the reaction mechanism for this particular reaction. Then we will be studying about how 1,5-dicarbonyl compounds can be converted to pyridine. Later on, we will study about reactions of pyridine. We will study two major type of reaction. One is the electrophilic substitution reactions and the nucleophilic substitution on the pyridine ring. So both these reactions actually occur on the pyridine carbon atoms. Afterwards, we will study about synthesis of pyrimidines. So here we will focus on pinner pyrimidine synthesis and the Biginelli reaction. So how this reaction can be used to convert simple starting material into pyrimidines. Then finally, we will study about some of the reactions of pyrimidine. Pyrimidine undergoes both electrophilic and nucleophilic reactions on the carbon atoms. So we will be looking at some of the examples of these reactions. Welcome to the session on pyridine and pyrimidines. So far we have seen about the 5-membered heterocycles. Now we are going to see about heterocycles with 6-membered rings. Some of the examples for 6-membered heterocycle are pyridine, quinoline, isoquinoline. Here we have one heteroatom. Pyridine has one heteroatom. Quinoline has one heteroatom in position number 1, and isoquinoline we have a heteroatom at position number 2. These are heterocycles, 6-membered heterocycles with one heteroatom, and we also have pyrimidine which are having two heteroatoms. So these are some of the compounds we are going to study. So pyrimidine is the example with two heteroatoms in a heterocyclic ring. Pyridine was first isolated from bone oil and it was highly stable, and they undergo substitution rather than addition reaction. So these are all some basic information about pyridine and some of these heterocyclic compounds. Let us look at some of the important pyridine derivatives which are used as a drug. Nicotine is present in tobacco, and some of the compounds are very important pyridine derivatives. Nicotine is present in tobacco. Sulfapyridine is an antibacterial agent. This has the pyridine unit. Pyridoxine is nothing but a vitamin B6 that is also having its vitamin. So this is a biomolecule. This is having a pyridine moiety. And quinine is a poisonous principle in hemlock. So if you look at all these compounds, this is basically the reduced pyridine structure or the saturated pyridine ring here. This is nothing but the piperidine. So if you look at all these compounds, we have some compound which are present in tobacco, which is actually toxic in nature, and we also have other poisonous compound which are having pyridine unit, and we have some good compound also like a drug or the biomolecule that is also having pyridine. So what we can say is pyridine is having a versatile nature, and this is also found in natural compound. This is a natural product. Let us look at synthesis of pyridine. The major approach to pyridine synthesis mainly involves around condensation reactions, because when we saw in the previous 5-membered ring formation, we have intramolecular reactions where the functional groups are present at the terminal. So similar to that, we have seen 4+1 approach to the 5-membered ring formation, and we also have studied about 5+1 approach to 6-membered ring. So here the condensation of dicarbonyl compounds or cycloaddition reactions are very crucial for the formation of pyridine also. In the case of CC bond formation, we will be studying about Hantzsch pyridine synthesis, and for the dicarbonyl compounds, we will be studying about 1,5-dicarbonyl compound condensation to give pyridines. So, these are some of the two major class of reactions we will be looking at for the pyridine synthesis. Let us start with the Hantzsch pyridine synthesis. So, this is actually an example of a multi-component reaction. That means there are various starting materials are involved that leads to the final product. So, here we have a aldehyde, we have a beta ketoester, and we have ammonia or ammonium hydroxide. All these three are condensed. So, when we talk about the dicarbonyl systems, this is not an intramolecular reaction, but this is an intermolecular reaction. So, we have one carbonyl unit, we have the second carbonyl unit, and we have the heteroatom. So, all the three units are involved in the product formation. So, if you look at here, we have the aldehyde unit, and we have the beta ketoester unit, and we have the heteroatom. So, all the three are involved. So, that is the reason when there are more than two components are involved in the reaction, we call that as a multi-component reaction, and this Hantzsch pyridine synthesis is an example of the multi-component reaction. So, this condensation under basic condition leads to the formation of a 1,4-dihydropyridine derivative, and this 1,4-dihydropyridine derivative on oxidation leads to the final pyridine derivative. So, here if you look at the pyridine unit has 5 carbon atoms and 1 nitrogen atom. So, how the distribution of carbon and nitrogen are given here in this particular case, like 2 of the carbon atoms from each beta ketoester, that means total 4 carbon atoms that are present in the pyridine ring comes from the beta ketoester. 1 carbon comes from the aldehydic unit, and the nitrogen heteroatom comes from ammonia. So, these are all the ways by which the heterocyclic ring is actually constituted or formed from the various starting materials. So, in this multi-component reaction, we have many questions to answer. We have seen that the reaction actually occurs under basic conditions. So, our first question is, can we carry out this reaction under actually neutral condition instead of basic conditions? Then when we talk about beta ketoester is involved, will the self condensation takes place under basic conditions? So, this is another question. The beta ketoester contains 2 units, that means it has a ketone, this is also having a ester unit. So, when we have these kind of multi-functional unit present in this compound, which carbonyl carbon actually reacts, whether it is the ester carbon or the ketone or both. So, this is another question we have to answer. And when we talk about this amino carbonyl condensation happens first or at last, because these are all individual units. So, these 3 units combine together to give the cyclic system. So, whether the nitrogen reaction occurs first or the nitrogen reaction occurs last. So, this is again we have to find out. And if the ammonia, which is a nucleophilic species, attacks the carbonyl carbon, which is the electrophile, does it attack the aldehyde or the ketone or the ester? Because we have 3 carbonyl units that is present in this particular system. So, this being a nucleophile, does it attack the aldehyde, or this attacks the ester, or it attacks the carbonyl? So, we have different questions to answer, and let us see how this reaction actually proceeds. So, if we look at the individual reactions that are involved in the formation of pyridine, we have a Novonigal condensation reaction to give the alpha beta unsaturated product. So, this is one of the reaction, and we also have a Michael addition, that is a conjugate addition of this alpha beta unsaturated product and the enolate of the beta ketoester. So, now you will be understanding how the reaction actually proceeds. So, first we have to form a alpha beta unsaturated product, and this alpha beta unsaturated product reacts with the corresponding enolate of the beta ketoester, and then the carbonyl ammonia condensation leading to the imine or enamine depending on how the reaction actually proceeds. And finally, this imine or enamine attacks the one of the carbonyl group leading to the cyclization. So these are all the crucial reactions that are the individual reactions involved in the dihydropyridine formation, and once this dihydropyridine is formed, then finally it has to undergo oxidation to give the corresponding pyridine derivative. And of course, when we talk about the biology, pyridine to dihydropyridine conversion is a very important biological reaction, and if you look at the dihydropyridine to pyridine formation, that is NADH to NAD plus formation, is a very crucial reaction in biological systems. So let us look at the mechanism of this Hantzsch pyridine synthesis. So we have two beta ketoesters. So this is one unit, this is the second unit. So two beta ketoesters are involved, and we also have the aldehydic component, and we also have the ammonia component. So these are all the various things that are involved, and the first step is the reaction which occurs at the basic condition, that is pH 8.5. So this is basically the aldol type condensation. We can actually call this as the Knoevenagel reaction. So this Knoevenagel reaction leads to the alpha beta unsaturated product. So that means 1 and 3 reacts first. So we have the aldol, and the anion is actually generated on this particular beta ketoester, and this attacks the aldehydic unit. So the aldol condensation leading to the formation of the alpha beta unsaturated system here. And in the simple aldol reaction, the aldol reaction condensation generally takes place between an aldehyde, two aldehydes, but here we have a beta ketoester and an aldehyde. So this is a Knoevenagel type reaction, and that leads to the formation of alpha beta unsaturated product. So once the alpha beta unsaturated product is formed, then the next step is the Michael addition reaction. So this is nothing but the 1,4 addition reaction. So we have a 1, 2, 3 and 4. So we have 1,4 addition that is happening. An anion is generated on the beta ketoester, and this active methylene hydrogen is highly acidic, so it is very easily removed by the base. So we generate an anion here, and this anion now adds to the alpha beta unsaturated compound, and this reaction is a Michael addition. So this leads to the condensation of 2 beta ketoesters and 1 aldehyde. So all the 3 are connected together here, and this is how the reaction or the intermediate is formed. And once this is formed, the next step is the amine reaction. So amine reacts with one of the carbonyl unit first to give the ene. So this is the ene unit, this is the amine unit. So this condensation, the condensation of ammonia with this carbonyl unit leads to the formation of an enamine derivative, and once this enamine is formed, this nitrogen is the nucleophile here, the electrophilic carbon is there. So this nucleophilic nitrogen attacks the electrophilic carbon, leading to the formation of the dihydropyridine after the loss of water molecule. And once this dihydropyridine is formed, we can actually carry out oxidation using nitric acid or other oxidizing agent to give the pyridine derivative. So this is the overall steps involved in the Hantzsch pyridine mechanism or Hantzsch pyridine synthesis. Let us look at how we answer all the questions what we have posed earlier. So the first question, can the reaction be carried out under neutral conditions? But we cannot carry out this reaction under neutral condition. The reason is the initial step is the aldol condensation. So there we do need to generate an anion. So generating anion under neutral conditions are going to be a little bit difficult. So that's the reason the use of ammonia actually makes the complete reaction mixture little bit basic. So that is the base which is involved in the initial step, and this reaction cannot be carried out under neutral condition because this does require some basic reagent for initiation. So, in the second question is, when the beta keto is involved, will self condensation takes place under basic conditions? Yeah, this question is a very valid question, and yes, this will happen. So, we have to carefully control the concentration of the substrate and the reaction parameters like temperature and the solvent. We can actually reduce this side reaction. We can reduce this side reaction, which actually affects the final product. So, the self condensation has to be avoided very carefully. So, how we can actually do that is, we have to control the concentration of the substrate, concentration of the base, and which solvent we are running, and at what temperature we are running this reaction. So, all those things can be used to control the self condensation of this particular beta keto ester. The next question is, if the beta keto ester undergoes reaction, so what is the place, whether it is the ester carbonyl or the ketone carbonyl or both undergoes reaction? So, if you look at the initial step, basically the anion is the one which is being generated in this reaction. So, that means we have the nucleophilic species is basically the beta keto ester's central carbon. And this is the reason we say when anion is generated, this anion can actually attack the carbonyl ketone of the same beta keto ester itself. So, that is the reason we have to control the concentration, so that the concentration of the esters beta keto ester remains comparatively low, so that the self condensation can be easily avoided. So, once the anion is formed, this anion can actually undergo resonance. So, we can actually form the enolate. See, this is the enolate. So, this is the en part and this is the ate part. So, en and ate, enolate is formed. So, this is the resonance stabilized one, because instead of the carbanion on this particular carbon, this can actually undergo resonance with the neighboring oxygen. So, that means this particular oxygen is not, this carbonyl is not free now. This is now involved in the resonance one. So, that is the reason we can very well say that this carbon is no longer going to be electrophilic in nature. So, if you look at the carbonyl carbon, or if you look at the enolate, this particular carbon always has the double bond. In other words, there is no loss of electron density on this particular carbon. So, this carbonyl carbon is not available for any electrophilic attack. So, once we have the enolate, this enolate now reacts with the corresponding aldehyde. So, that means the carbonyl unit from the beta keto ester is not involved in any of this reaction. It is the aldehyde carbon that undergoes the reaction. So, we end up with this particular condensed product, and once the charge reversal takes place, with the concomitant removal of a water molecule, we end up with the alpha beta unsaturated system in this particular intermediate is formed. So, what we can say is, in this particular case, the beta keto esters carbonyl group or the ester group are not involved in the first or the initial condensation reaction. So, the next question is, does the amino carbonyl condensation happens first or later? So, let us assume if the amino condensation happens first, that means basically the aldehyde will react with the ammonia as shown here. So, this will lead to the imine formation. So, once the imine is formed, it cannot undergo this corresponding reactions, further reactions with the carbonyl compound to give the dihydropyridine. So, this is not possible. This reaction will completely stop. So, in other words, when we write the mechanism, we cannot, or we generally do not want the imine to be formed in the first place. So, that is the reason this reaction does not occur first. And of course, if we look at the reactivity of the aldehyde and the beta keto esters, we already know aldehyde is much more reactive than the beta keto ester. So, generally how the people generally carry out the reaction is, they first condense both the beta keto ester and the aldehyde first. And when this condensation takes place first, then we have the required product that is ready to undergo reaction. Then we can actually add additional amount of ammonia to facilitate this particular reaction. So that is the reason we generally prefer, or the reaction how it proceeds is the condensation of the beta keto ester and the aldehyde happens first. In some examples, it is also possible to make the enamine first. That means the reaction between beta keto ester and ammonia separately, and this can be allowed to react with the enone. So this is also possible. So this is a different reaction. Instead of aldehyde undergoing reaction with the amine, the beta keto ester can actually undergo reaction with the ammonia to give the enamine, and this enamine can now react with the alpha beta unsaturated system that is formed by the condensation of beta keto ester and the aldehyde. So this is possible. So the beta keto ester and aldehyde condenses to give the alpha beta unsaturated compound. So this is one. The second unit of the beta keto ester can be reacted with ammonia to give the corresponding enamine. So these two can be formed separately, and these two can be reacted together to give the final product. So in this particular case, what we can very clearly say is aldehyde reacting with ammonia is not the preferred reaction and it does not take place, but the beta keto ester can react with ammonia in the beginning, or this cyclization can also happen at the later stage. So here let us come back to that. If the ammonia is the nucleophile that attacks the carbonyl carbon, does it attack the aldehyde, ketone or ester? We have seen that aldehyde attack does not take place. If the aldehyde attack actually takes place, then the reaction may not proceed. So this doesn't happen, and in the case of ester also that reaction does not happen, because we have seen only the ketone that forms the enamine. So in other words, we can also look it from a different direction. So in this particular case, this particular ketone can react with the ammonia to give the enamine, and that enamine now can undergo reaction with the second carbonyl carbon to give the cyclized product. So that means ketone is actually much more electrophilic in nature than the ester. So that is the reason ammonia reacts only with the ketone part and not with the ester carbonyl. So this is how we can actually rule out that aldehyde reaction is not happening, ester condensation with ammonia is also not happening, only the ketone that undergoes the reaction with ammonia. So this is how we can actually rule out how the reaction actually proceeds. And we have also seen that it can easily form the enamine with one of the ketone, and once the enamine is formed, then that undergoes the reaction with the second ketone to give the cyclized product. So in this particular reaction, the most crucial partner which is involved in the reaction is only the carbonyl ketone. That means ketone carbonyl is the one which is involved in the reaction. And in the case of aldehyde also, we can say it is the aldehydic carbon that is involved in the reaction. So in all these cases, the presence of ester, then why do we need to have the presence of ester if it is not at all undergoing in the reaction? But the presence of ester, actually this is a electron withdrawing group, we know. So when there is an electron withdrawing group, that actually increases the acidity of the carbon. The central carbon's hydrogen are becoming highly acidic in nature. So that means a mild base can be easily used to abstract this particular hydrogen. So that is one of the reason the electron withdrawing group, that is ester group, is used. If we only have a carbonyl unit, if we simply have a carbonyl unit, then in that particular case this carbon is not having a highly acidic proton. So that is the reason this cannot be easily generated, or the anion cannot be formed very readily. But if we have a another electron withdrawing group that is present here, then that actually facilitate the removal of this acidic hydrogen very readily. Now the next question may come. So instead of ester, we can also have a ketone. So if we have two ketones and if it is an unsymmetrical ketone, then what will happen is all the carbonyl, that is the ketone, can undergo reaction. So we will end up with a mixture of product. So it may be the self condensation, it may be the cross condensation. So that means the number of product that will be formed in this reaction going to be very high, and this is not going to be a useful method for preparing our desired pyridine derivative. So that is the reason an ester group actually helps in facilitating the reaction without participating in that particular reaction. So that is the reason the ester group is actually used. And if you look at the last step, which is the oxidation, and what is the driving force for this reaction is very important to know. Here we are showing that reaction using DDQ, that is dichlorodicyanoquinone is used as the oxidizing agent, and here the crucial step is the hydride transfer reaction. So this is one of the reaction which is used in the NADH reaction also, NAD plus NADH reaction. Here again the hydride transfer is the crucial step. So instead of hydrogen or a proton, the hydrogen with its bonded electron, that is the hydride that is being transferred to the oxidizing agent. So this leads to a positive charge on this particular carbon. So the double bond actually shift towards this particular carbon, and the lone pair from electron from the nitrogen actually comes between these two. So we end up with a H plus ion. So this is what is called in the biological system, it is basically the NAD plus which is formed. So the formation of NAD plus, and this is actually the NADH, is the crucial redox reaction that is involved in various oxidation reactions which are seen in biological systems. So this loses a proton, this NAD plus moiety, which is a pyridine with plus charge, loses a proton to give the final pyridine, which is aromatic in nature. And if you look at the DDQ, this actually takes the hydride ion, and then this loses, there is a transfer of hydrogen, proton transfer takes place, and we end up with the final product. This is a aromatic product. So if you look at the starting material, this is a non-aromatic, or there is no aromatic system present in this DDQ, but after the hydride is transferred, we end up with a system which is aromatic in nature. So the formation of two aromatic product as the final one is the driving force for this reaction, and this oxidation takes place very readily because of the formation of two aromatic products. So that's the reason the DDQ is generally used for oxidation, which is a very mild reagent. And there are also other methods of synthesis of pyridine. So here we will see the 1,5-dicarbonyl compounds and ammonia condensation. So this is what we have talking about earlier also. If we have a 1,5-dicarbonyl system, and if we treat that with ammonia, will we get the pyridine derivative? Yes, this reaction also proceeds with the loss of two water molecule. We end up with a dihydropyridine unit. This can be oxidized to give the final product. The pyridine can be formed. Of course, the product yield for these reactions are much lower compared to the Hantzsch pyridine synthesis what we have seen earlier. So here also we have a NME2 system which reacts or undergoes condensation with the carbonyl compound, and here again we have a 1,5 system with one ring present, and when we carry out the dicarbonyl condensation with ammonia, we actually end up with a bicyclic system as shown here. Here we have the substituted pyridine as our final product. So the reaction can proceed by two methods. One, the dicarbonyl compound can be condensed with ammonia in ethanol, that gives the dihydropyridine derivative, which an oxidation gives the pyridine derivative, or we can also use hydroxylamine. So, the dicarbonyl compound can be reacted with the hydroxylamine to give the corresponding NOH derivative, which loses water molecule to give the final product. So, these are all the two methods by which this product can be easily formed. When we look at the reactivity, compared to the benzenoid compounds, these are electron deficient. So, this we have seen whenever we introduce a nitrogen atom into the benzene ring by the replacement of one carbon and hydrogen, that makes this particular pyridine ring electron deficient, because nitrogen is electronegative in nature, we have seen that. So, because of the introduction of an electronegative atom into the 6-membered ring, this pulls the electron away from the ring. So, that means what happens is the electron density available on the carbon atoms becomes less. So, if you look at the electron density in benzene, we exactly know all the 6 carbon atoms are having the electron density as 1. So, that means 1, 1, 1, 1, 1, 1. So, they have the uniform electron density distribution around the benzene ring. So, the 6 pi electrons are actually distributed equally. That is the reason the reactivity of benzene ring is there is no selectivity of reactivity, and all the positions undergo electrophilic substitution uniformly. But when we come to the pyridine ring here, so the carbon, if we look at each carbon, they are supposed to have only 1 pi electron density. Instead of 1, they are having only 0.95, and in this position, this is the 4 position, this is 3, this is 2, and this is 1. So, when we number, the heteroatom gets the lowest number. So, 1, 2, 3, 4, if you look at the 2 position and the 4 positions are having less electron density, and the 3rd position is having little bit higher pi electron density. So, that is the reason whenever pyridine undergoes reaction, we can very well say there is going to be some regioselectivity in that particular reaction, and moreover this also clearly tells that the pi deficient nature of pyridine ring. And as we know, the electron withdrawing, inductive and mesomeric effect of nitrogen is responsible for the reduction of pi electron density on the aromatic ring. So, nitrogen is electron withdrawing. This actually withdraws electron through inductive effect as well as mesomeric or resonance effect. And because of this mesomeric or the resonance effect, we see C2 and C4 positions are having much less electron density compared to C3 position. So, that is what is very crucial for the reactivity. And it is also possible that pyridinium cations also exist. Acylation of pyridine can be carried out at a very low temperature at -78 degrees centigrade. So, we have different reagents that are generally used for the acylation reactions and other reactions. So, acyl halides and chloroformates reacts instantaneously with pyridine to form the pyridinium salt. So, here we have the acyl halide. Here we have the chloroformate. So, the chloroformate and acyl halides reacts with pyridine to give the corresponding derivative pyridinium salt, and we can also react sulfonyl chloride and anhydrates to give pyridinium salt. So, the sulfonyl chlorides or anhydrates also, and anhydrates also react with the pyridine to give the corresponding pyridinium salt. So, this is a different reaction compared to pyrrole. When we saw in the case of pyrrole, pyrrole does not undergo N-acylation or N-alkylations that readily, whereas in the case of pyridine, the N-acylation or the N-sulfonylation reaction happens very readily. So, let us look at the next one, which is the electrophilic attack at carbon atom. As we have seen, this pyridine ring is having less electron density on the carbon atoms. So that is the reason they can actually undergo electrophilic attack, and this electrophilic attack at a different position or can be explained by the different electron density. So the presence of electron withdrawing nitrogen actually pulls the electron out, and that makes these heterocycles less reactive than benzene towards electrophiles, because in the case of benzene we exactly know that all the carbon atoms are having the pi electron density as 1, whereas in the case of pyridine it is less than 1. So that means the reactivity also going to be lesser than benzene, and this effect is actually pronounced at position 2 and 4. That's what we have seen. So the 3 position is having a little bit higher pi electron density compared to 2 and 4. That means the electrophile will preferably attack the 3 position. So this we can actually look at from the pi electron density, and we can understand. And when the electrophile attacks under acidic conditions, the reactive species is either a small amount of free base or the less reactive conjugate acid. So this is one of the things, because in the presence of proton can also be considered as a electrophile. But when the reaction occurs under acidic conditions, what generally happens is the nitrogen is actually protonated in the beginning. So that means the electrophile first attacks the nitrogen atom. So that is the reason the reaction does not proceed that readily in the case of electrophilic substitution if they are carried out under acidic conditions. But if only the electrophile is added, then it undergoes preferentially the attack at the 3 position. So that is the reason we have to always be very careful when we carry out the pyridine reaction. Try to avoid acidic conditions, especially the protic acidic condition should be avoided. Let us look at the electrophilic attack at the carbon atom. So we have seen that electron density, pi electron density at the 3 position is higher compared to position number 4, followed by position number 2. So that is the reason the reactivity also seen in the same case, like when we look at the halogenation reaction. So the 3 position undergoes reaction very fast, followed by 4, and then 2 position substitutions are very less. And pyridine, if it has electron donating substituents, then the chlorination can happen very readily, and the chlorination occurs at the positions ortho and para to the substituent. This is also possible. We have a electron releasing group, that is hydroxy is present, and when we subject this to the chlorination reaction, so the product, this is a para product and this is the ortho product. Ortho to the hydroxy group, para to the hydroxy group. So this is the electron releasing group. So whenever there is an electron releasing group, then the chlorination in this particular case happens at the ortho or para position. So if you look at the ortho position, this is the major product with 87%, and of course we have 3% of the para product also, and the di substitution, that means ortho and para substitution also happens, we get 10% of the product. So this is one way of telling whenever there is an electron releasing group, that increases the substitution reactions on aromatic systems. The next one is a bromination reaction. So when pyridine is treated with bromine at a 65% oleum, we get a ortho substituted product, especially to the substituent, or in other words what we can say is this is the 3 substitution. So the electrophilic substitution preferentially occurs at 3 positions compared to, here again we have the di substitution. So when the 4th position is actually blocked, then that actually prefers the 3 substitution as the major product, like 81% of the product is formed. And when there is no substitution, obviously we end up with the mono substitution as only 21%, but the di substitution happens, and if you look at mono and the di substitution, the reaction actually occurs at only the 3 position. So the 2 or 4 position products are not at all formed in this particular case. So whether it is a mono substitution or a di substitution, both occurs at position number 3 only. And we have seen this also as an earlier examples with the halogen atom. Chlorine was also present. So in the bromination reaction, if electron donating group is present, then preferably the ortho substituted and the ortho and para substituted products are formed, and we also get some amount of diortho substituted product. Because pyridine is highly electron deficient, so we cannot use the nitration reactions very readily. In other words, nitration of pyridine is very difficult, and of course the presence of electron donating substituents like methyl, hydroxyl or amino unit increases the pyridine towards the nitration reaction. So like the bromination, we can also use the hydroxy substituted pyridine to undergo nitration very readily. Only if there is a electron donating group present in the pyridine ring that undergoes nitration reaction. So this is a very unique reaction to pyridine. Basically, benzene does not undergo any nucleophilic substitution reaction, but pyridine undergoes nucleophilic substitution reaction because the pyridine ring is actually pi electron deficient in nature, that we have seen earlier also. So that is the reason, because of the pi electron deficiency of the pyridine ring, this undergoes nucleophilic reaction very readily. When we carry out the nucleophilic chlorination of pyridine, this occurs at position 2, 4 or 6. Because the position 2, 4 and 6 are the places where we have already seen they are having the lower electron density. So the nucleophile can easily attack those places compared to 3 positions. So when a electrophile attacks, the electrophile always attacks the electron rich place, and if it is the 3 position is the electron rich place in the case of pyridine, so the electrophile attacks the 3 position. But if it is a nucleophile, this prefer to attack the electron poor position. So position 2 or 4 is the electron deficient carbon atom. So that's the reason nucleophile attacks 2 or 4 position. So that is the reason if you look at the nucleophilic attack, we have the 2 substitution or the 4 substitution that is formed in the case of nucleophilic attack. So here we have the pyridone which undergoes reaction with the POCl3 to give the or introduce the chlorine into the pyridine ring. When acetyl hypochlorite is reacted with pyridine, we end up with the 2-chloropyridine as the major product, and of course we also end up with some quantities of 2-acetoxypyridine as the minor product. Let us look at pyrimidines. So pyrimidines and pyridines are 6-membered heterocycles with 2 nitrogen atoms. So here we have, if it is a 1,2 substitution, they are called pyridines. If it is 1,3 dinitrogens or di substitution, they are called pyrimidines. And 9H purine is basically having the 1,3 di substitution in the 6-membered ring. Pyrimidines and purines are the nitrogen bases which is present in DNA and RNA. The names of purine nucleosides end in osin and the names of pyrimidine nucleosides end in idine. So the purine numbering is actually different. This is an exception to the systematic numbering what we follow in heterocyclic chemistry and in IUPAC nomenclature. So this is generally being followed by biologists, so these numbers are not actually changed. If we have to actually start from the numbering, we have to start from the nitrogen which is actually adjacent to the ring junction. So this is going to have the lowest number, but unfortunately this compound is called as a 9H purine. The ring junctions are generally not numbered in the heterocyclic nomenclature or IUPAC nomenclature, but biologists generally were using this particular numbering to name the compound. So that is the reason this numbering 9H purine is an exception to what is being followed in heterocyclic chemistry or organic chemistry. At least you should know that, because biologists follow a different numbering for the case of purines. Here some of the pyrimidines are given. Cytosine, thymine and uracil are the examples of our pyrimidine unit that is present in both DNA or RNA. Let us look at the synthesis of pyrimidine. we start from malonic ester. The malonic ester is treated with urea in the presence of a strong base and under heating condition, that leads to barbituric acid formation. So, this barbituric acid can undergo resonance. This actually undergoes tautomerization because one of the hydrogen from the nitrogen is shifted to the oxygen. So, this tautomerization leads to pyrimidine derivatives, and this on treatment with the POCl3 is converted to the chloro derivative, and this chlorine can be removed by treatment with the zinc dust, which gives the pyrimidine. Unsubstituted pyrimidine is formed. So, this is a reaction where we have a pure pyrimidine without any substituent. Another method is the Pinner-pyrimidine synthesis. Here 1,3-dicarbonyl compounds are reacted with amidines in the presence of potassium carbonate. Here we have a tri-substituted pyrimidine that is formed in this reaction. Depending on the substituents what is present in the dicarbonyl compound, we end up with the substituted products as pyrimidine derivatives. And there is another reaction which is called Biganelli reaction. So, in this particular reaction, an aldehyde and 1,3-dicarbonyl compound is reacted with urea. So, these are all the three, and since three different starting materials are used, so this is an example of multi-component coupling like what we have seen earlier for the Hantzsch-pyridine synthesis. In the case of Hantzsch-pyridine synthesis, we have an aldehyde, we also have a beta keto ester, but in this particular case we only have a amine unit when the pyridine is being formed, and if it is a 1, 2, 3, because we have a 1, 3 dinitrogen present in our final pyrimidine. So, that is the reason the starting material also need to have this kind of arrangement. So, we start from the urea unit, and 1 carbon comes from the aldehyde and 2 carbons comes from the beta keto ester. So, that is how we can actually say how the 6 atoms which are present in the pyrimidine moiety is assembled. And reaction with polystyrene sulfonic acid at 100 degrees centigrade, (80° centigrade) leads to the pyrimidine derivative as shown here. And let us look at the resonance of pyrimidine, because before we understand how the pyrimidines can undergo reaction, we need to understand how the resonance exists in pyrimidine. We have neutral structures without any charge. These are all the 2 resonance structures that are possible for pyrimidine, and we also have the charged structures for pyrimidine. So, these are all the various structures which are possible for the resonance. This happens due to the electronegative nitrogen. So, in one of the case, the double bonded electron is pulled by the nitrogen because nitrogen is electronegative in nature. So, this shift towards the nitrogen, making this carbon electron deficient. So, since there is a electron deficient carbon near a double bond, this double bond shifts between nitrogen and carbon. So, this particular carbon now gets a positive charge. So, there is a shift of pi electrons from this particular double bond towards the carbocation. So, now this carbon gets the positive charge. So, this is how the various resonance structures operate, and there is a negative charge on nitrogen and there is a positive charge on the nearby carbon. So, this can actually this double bond, the negative charge on nitrogen can come between the carbon, the carbocation and this nitrogen, that leads to a neutral structures as shown here. And similarly, we can also start from the other nitrogen. So, here we started from the bottom nitrogen. Instead of bottom nitrogen, we can also start from the top nitrogen. So, when this also can undergo similar resonance structures, similar 3 resonance structures are possible for this nitrogen having negative charge. So, these are all the various resonance structures that are possible for pyrimidine. And when we look at the reactivity of pyrimidine, pyrimidine is weakly basic with the pKa of 1.3. These reactions can occur at nitrogen, and the reaction can also occur at carbon. So, there are two places where the reaction can occur. The carbon can undergo electrophilic and nucleophilic reactions, and of course, nitrogen can also undergo quaternization reaction. So, this is an example of reaction at nitrogen. So, here the reaction with methyl iodide or reaction with borate anion, tetrafluoroborate anion, these two leads to the substitution on nitrogen. Methyl iodide adds to one of the nitrogen if you use one equivalent, and triethoxyfluoroborate when we use, that can actually add two ethyl groups to both the nitrogen atoms. So, these are the quaternization reaction which occur on nitrogen. So, as we have seen, electrophilic reactions are possible for the carbon. So, here bromine in the presence of nitrobenzene at 130 degree undergo reaction to give the C electrophilic substitution. That means the bromine is added to the ring, and this is one of the example where the carbon undergoes electrophilic reaction. And for nitration and chlorination to occur, the presence of electron releasing groups are needed. Like similar to the pyridine case, we do need a electron releasing group. So, here we have the hydroxy unit. Once the hydroxy unit is present in the pyridine unit, pyrimidine unit, then this can actually undergo nitration reaction as shown here. So, we end up with the corresponding nitro derivative. So, for these kind of electrophilic reactions to occur, we do need a activated group that is present in the pyrimidine unit. And when we talk about the nucleophilic reaction, so in the case of pyrimidine, the nucleophilic attack may take place at 4, 6 or 2 positions. So, this is a Grignard reagent or a similar type of reagent, which is the nucleophile which is going to attack the pyrimidine ring, and here this reaction leads to the introduction of a alkyl group as shown here. So, the metal based reaction is an example of a nucleophilic addition reaction, especially reaction with phenyl magnesium bromide as shown here gives a 4 substituted derivative. That means the phenyl group is introduced at the 4 position, and this can actually undergo oxidation to give the aromatized derivative. So, this is also leading to the pyrimidine derivative, and these are the examples of nucleophilic reactions which occur on pyrimidine ring. So, both electrophilic and nucleophilic reactions are possible on pyrimidine, and all these reactions occur on the ring carbon atom only. Let us recap in the summary what we have studied. We have studied about the synthesis of pyridine. We studied elaborately about the Hantzsch pyridine synthesis and its mechanism, how the beta keto esters, aldehyde and ammonia condense together to give the pyridine we have seen. So, the initial reactions actually proceed through the aldol type reaction to give alpha beta unsaturated system, and then we also have studied how the Michael addition reaction happens, and finally how the ammonia condensation takes place between the carbonyl units, that is the ketone units, to give the dihydropyridine, and how the dihydropyridine is finally oxidized to the corresponding pyridine we have seen. We also have seen about the 1,5 dicarbonyl compound addition condensation reactions to give pyridine derivatives. We also studied about the various reactions of pyridine. Pyridine is quite unique compared to benzene. Pyridine is basically the pi deficient system. So, due to the pi deficiency, how the reaction specifically occurs, especially the electrophilic substitution occurs at 3 positions we have seen, and what are the electron density distribution that is present in the carbon atoms of pyridine we have seen, and we also saw how the nucleophilic attack on pyridine leads to different type of product. So, the electrophilic substitution preferentially happens at 3 position, and the nucleophilic addition actually takes place at 2 positions. So, all those things we have seen. We also studied about the synthesis of pyrimidines. we studied about pinner pyrimidine synthesis and the Biginelli reactions. So these are all the two reactions we studied about how pyrimidines can be synthesized. Later on we saw the reactions of pyrimidine, what is the resonance structures of pyrimidine, and how the electrophilic and the nucleophilic attack on pyrimidine takes place, leading to different products we have seen. And in this particular case also, due to the pi deficient nature, only the carbon atoms in the ring undergoes reaction, and the nitrogen actually undergoes only the quaternization reactions in the case of pyrimidine. So all these things we have seen. With that we conclude this session. Thank you.